Okay, so welcome to chapter 9. And so in chapter 9, we are going to do what we've been doing when investigating one particular population by looking at a sample from that population. We are now going to consider looking at two populations at the same time, taking samples from each of those populations, and then using the samples from two different populations to compare those two different populations. So these won't be two samples from the same population. We need to have two separate, clearly defined populations and then take samples from each one of those populations in order to compare. So let's just start with a simple example in mind along the lines of what I've been saying all along. I've been talking about in general something like I want to know on average how tall students at DVC are. So let's say instead that I wanted to know on average how much sleep students at DVC get. And so I would be thinking about taking a sample of students from DVC and asking them on average, how many hours of sleep do you get a night? So that would be something where I have one population, students at DVC, and I take a sample and then I learn something about that sample, which I then use to infer about the population. So what if I instead said, well, I wonder if students at DVC are able to get more sleep than students at Los Medanos College, one of our sister schools. Well, that's a different population. I'm now talking about students at a different school instead of DVC students. So what I could do is I could take a sample of DVC students and a sample of LMC students, and then I could look at those two samples' results to then try to draw conclusions and compare the sleep on average of students from one school compared to the other. And so the simple kind of comparisons that we will make would be, I believe students at DVC get less sleep than students at LMC. And so I would take samples from each, and those samples don't have to be the same size. I could maybe get 50 students from DVC and 78 students from LMC, who knows? But I could look at the average amount of sleep that my samples got from those populations. And I would think that if the average sleep from my sample of DVC students was less than the average amount of sleep from my students sampled from LMC, that maybe that would support the claim that DVC students get less sleep than LMC students. But that would depend how much less was it? Were they kind of close to equal? Was it LMC students got 8 hours and DVC students got 7 hours and 50 minutes? Well, that's not much less for me to say that I think that's true for the entire populations from the two schools, because those are pretty close. But if the average LMC student was 8 hours and the average DVC student was 5 hours, well, that's a very, very big difference. So I would say, wow, that seems to support my claim that DVC students get less sleep than LMC students, as an example. So we are going to be making the same kind of claims we did before. We're going to be making hypothesis tests, but instead of targeting a particular value of a population and making a claim about that, we are going to target two populations and compare and make a claim that one is bigger than the other, one is less than the other, or that they're the same or not the same. And that would be one-sided tests or two-sided tests, just like it was in the past. So in order to do this, we need to set up notation. We need to set up the idea about what the formulas will be calculating. Of course, we won't be using the formulas. We'll use StatCrunch instead. But that's the basic idea. So let's see how the slides describe this key concept. Well, here's our 4 sections. So let me point out, we are only covering the first 3 sections of this chapter. The 4th section would be perfectly good for us to cover. It's just not really crucial, and It's an optional section, so we are opting not to do it in order to focus our time on other things. So we will not be comparing two variances or standard deviations. We instead are going to stop with section 3, where we compare two dependent samples or matched pairs. So in 9.1, which we'll talk about now, we introduce this idea of comparing two populations, but we do it by focusing on comparing proportions from two populations. And then in 9.2, we'll compare two means from populations. And then we'll talk about a different type of comparison in 9.3 when you have matched pairs of data. So in 9.1, we're looking at two proportions, and here's our key concept. In this section, we present methods for 1, testing a claim made about two population proportions, and 2, constructing a confidence interval estimate of the difference between two population proportions. The methods in this chapter can also be used with probabilities or the decimal equivalents of percentages. All right, so let's get into it a little bit, and then we'll look at some notation and talk about mathematically the idea of how we do this comparison. So our objectives for these inferences about two proportions is 1, that we can conduct a hypothesis test of a claim about two population proportions. So what would be an example? Perhaps a claim that DVC students have a higher proportion that wear blue clothing. Than does LMC. So there's a claim where I'm claiming something about the proportion of the DVC student population compared to the proportion of the LMC student population. So I have two different populations, and I have a proportion from those populations, and I'm comparing and saying one is bigger than the other. And so I could collect a sample of DVC students and a sample of LMC students, look at the DVC sample, see what proportion of my sample was wearing something blue, do the same thing from the LMC students, and then based on those numbers and the size of both samples, I would try to see, based on a p-value and a significance level, whether the samples that I got from the two populations supported my claim that a higher proportion of DVC students wear blue than LMC students. All right, so that's an example claim that could be tested with a hypothesis test. Then it says also an objective is to be able to construct a confidence interval estimate of the difference between two population proportions. So here would be what an example of what you would have constructed. I could say that the proportion of DVC, I said C, DVC students that wear blue is greater than that of LMC by between 3% to 8%. So again, a confidence interval is a range of values. And in this case, you would be a confidence interval estimating the difference between two proportions. And so the difference will be how much bigger one is than the other. So if I think more students at DVC wear blue than students at LMC as a percentage of their population, that's what a proportion is. Well, then the question might be, well, how much more? Is it 10% more? Is it 15% more? How much bigger is the proportion of DVC students than LMC students? That would be some number that is the difference between the two proportions. And so then I could give a confidence interval, which would be a range of values where I would say that I have some confidence level, like if it's a 95% confidence level as a default, I could say something is like, I'm 95% sure that the actual difference between the DVC students' proportion of blue wearers and the LMC students' proportion is somewhere between 3 and 8%. That the population of DVC students that wear blue is greater than that of LMC by something between 3 and 8%. Questions, comments about that? All right, so this is the idea of how we will use statistics to compare two different populations. And this is very, very common. I'm giving these sort of silly, trivial examples, but in the real world, a lot of times we want to know things like if on average in a particular profession, in that profession, do men earn more than women? In average in society, is there a higher proportion of a certain minority that gets pulled over by cops for traffic tickets than the general population, or than a different minority, or than the majority? So there's all kinds of situations for both sociological reasons, for financial reasons, for scientific reasons, when you want to compare two different populations, two different groups, and compare something about them, some average value or some proportion. All right, so having said that, on we go. So they're going to introduce a bunch of notation. I'm going to focus on one element of that because we do need to be able to read through, but they're going to show us a bunch of stuff for formulas and stuff that we're not going to really use. So the key thing I'm going to point out here is that for population 1, they use little subscripts of 1 for all of the letters. And then for population 2, they just put a little subscript of 2. And then other than that, the letters are pretty much the same. So you have P for proportion, N for sample size, things like that. So here they talk about pooled sample proportions and things like that. And they have these formulas, and they have X1 and X2. And again, that's sample 1, sample 2. We're going to see if we can get away with not looking really at any of these formulas. So let's talk about the inferences about two proportions and what the requirements are. So they're basically similar to the requirements when we only had one sample and one population, but you have to apply it to both now. So we need to have a simple, some sample proportions are from simple random samples. Both samples have to be simple random samples. Bad data means bad results. The two samples are independent. So this is unique. Since we are taking two different samples, for comparing two proportions from two different populations, we have to make sure that the samples and the way they were collected were not connected in some way. And the way they describe that here is that the samples are independent. Now, we are going to look at situations where the sample values are connected. That's in 9.3. But in 9.1 and 9.2, we're doing a different kind of statistical study in which we are considering just two different populations. We consider them separately and then compare the results afterwards. And so, for example, if I was comparing the population of men and women, I would not want to do that by collecting data every time I ran across a married couple of a man and a woman. Even though that would be a quick way I could get data from a man and from a woman from my two different samples, the fact that those data values came paired in a dependent way would possibly bias the data. For example, I wouldn't get people that weren't in a man-woman marriage coupling. I also would be getting men and women connected together with their data values who chose to get married. For example, if I'm looking for blue wearers, maybe people who like to wear blue marry each other. And maybe that would bias my data in any event. So we want to just have a totally separate random sample from one population as we do from another before we make the comparison. And when we do things differently than that, we'll discuss that in 9.3. And then lastly, this was a condition that we had also for one sample. For each of the two samples, there are at least 5 successes and 5 failures. That had to do with the idea of using a normal distribution as an approximation for a binomial distribution. But in any event, we have that same requirement. So having gotten that out of the way, then having gotten this formula junk out of the way, I will point out, just as a reminder, when you are doing a proportion statistics, we are talking about a z distribution and a normal z distribution for proportion statistics. And I will also point out that as we were discussing, the way we do a comparison between two proportions is we think about the difference between the two proportions. So the key statistic is, instead of just doing a p-value, we're doing the proportion from sample 1 or population 1 and the proportion from sample 2, and what is the difference between the two. And so what's assumed in a null hypothesis is it will always be that the null hypotheses for all of our comparisons like this is that there's no difference between the populations, proportions, or mean values. And then the alternate hypothesis will always be that one is bigger than the other, one is less than the other, or that they're just simply not equal to each other, as it was in the past. But we'll be talking about the differences between the two, as opposed to a p being equal to a particular value. We will never, for our work in this class, say the difference between the two is equal to a number other than 0. It'll always be there is no difference between the two as our null hypothesis. So having pointed that aspect out, and then just trying to ignore the rest of the formula discussion there, they will also point out, as we saw in chapter 8, that there are kind of 2 approaches to hypothesis testing. You can use the p-value approach, or you can use the critical value approach. As usual, we prefer and like the p-value approach a little better. It's a little bit more intuitive, and of course, StatCrunch does the p-value work for us. Critical values can also be determined on StatCrunch, and there might be some problems involved that, and samples of that will be covered as well. But in general, it's best usually to start trying to understand the idea with the p-value approach. Again, more formulas about how to calculate a confidence interval, and they involve what they did before. So without getting too much into how we would use these, notice that they produce some margin of error, as we had back in chapter 7. And then the way you get your confidence interval is you take the value from your sample, and in this case, it's the difference between 2 samples. And you get a larger value of your confidence interval by taking that and adding the margin of error. And then you get the lower value of a confidence interval by taking the test values and subtracting the margin of error. So the process is still the same, but the margin of error looks worse because they have stuff from both samples. And also the middle value isn't just a single p-value, but it's the difference between your 2 sample p-values. But this process is how you would get something like the DVC students are greater in proportion of blue wearers than the LMC students. The difference between the two is somewhere between 3 to 8%. When testing the claim about the 2 population proportions, the p-value method and the critical value method are the same, but the confidence interval method is not completely equivalent. It sometimes produces a slightly different answer. And this is something we saw before, but they'll just have us do these directly, so you don't have to worry too much about that. All right, so let's focus on the hypothesis test in this introduction a little bit, and then of course we'll have to see this in action. For tests of hypotheses made about 2 population proportions, we consider, as I was saying just a second ago, we consider only tests having a null hypothesis that says that the difference between the two is equal to 0 because the proportion of 1 is the same as the proportion of 2. Again, P sub 1, P sub 2 is the proportion of population 1 and the proportion of population 2, respectively. So the null hypothesis is always P1 equals P2, and I'm going to write or P1 minus P2 equals 0. As we saw before, sometimes they'll translate that as a difference when we are looking in StatCrunch. So when we go to StatCrunch, we're going to be seeing it as a difference when we use the StatCrunch tool. With the assumption that P1 is equal to P2, the estimates, and again, this is the sample proportion, number 1. The estimates of P hat sub 1 and P hat sub 2, that's the proportion from sample 1 from population 1 and the proportion from sample 2 from population 2, are combined to provide the best estimate of the common values. And that combined value is the pooled sample proportion given in the preceding slides. So if you were going to just make a point estimate for the entire population, you would just add those two results together for one big result, which is what they were describing here in the pooled example. They have the pooled example here. But again, StatCrunch, thank you. We don't have to worry too much about this. So then here is their example, and maybe we'll look at this for a couple minutes and see if I can take a quick look on a Chapter 9 homework problem. Proportions of cars with rear license plates only. Are the proportions the same in Connecticut and New York? So this is a proportion problem. Those are two different populations, two different states' cars. Connecticut and New York are contiguous states, both having laws that require front and rear license plates. The proportion of Connecticut illegal cars with rear license plates only, when they took a sample, was 239 out of 2,049, or 11.7%. That's the proportion. Whereas in the proportion in the sample they took from New York turned out to be 1.6%. That's a lot less. Now let me have you note, these were two different sample sizes. They looked at over 2,000 cars in Connecticut and only 550 cars in New York, but that's okay. There's no requirement that your two samples are the same size as long as they're both big enough to give you the information you need. The sample percentages of 11.7 and 1.6 are obviously different, but are they significantly different? Meaning, are based on those sample sizes and how far apart the proportions of our samples were, is that sufficient evidence to support a conclusion or a claim that New York cars are illegal at a lower rate or have a lower proportion of illegal cars? They were definitely lower in the sample, but again, that's always something where we need the math to back up whether, and we need to know what significance level, 1% significance level, 5%, etc. So they tabulate the results here, and this is the kind of way you may get data in problems, is they might give you little tables like this. They show the proportions that were calculated, and then it says use a 5% significance level in the p-value method to test the claim that the Connecticut and New York have the same proportion of cars with rear license plates only. So the claim that they're testing is that the two states have the same proportion, and the difference from these samples, that just occurred by random chance. Obviously, these samples and no samples would support of a claim of equality, but the question is the difference between these two based on their sample size, is the difference in the two large enough to reject the claim that they have the same proportion, and instead support a claim that they don't have the same proportion? So they state briefly that they meet the requirements. These are simple random samples that are independent. And they say, all right, we set up our null and alternative hypothesis. So the null hypothesis would be that they're equal. And the alternative in this case, since that's the claim is that they're equal, the alternative would simply be that they're not equal. And at a 5% significance level, that means we would want a p-value, the probability that our samples came out the way they did, assuming that they're really the same. We'd want that probability to be less than 5% to reject the idea that they're really the same. So it says the following steps can be circumvented by using technology, which is what we're going to do. So I'm going to circumvent that step. Oh, thank you. Goodbye. I'm going to circumvent that step. Does anybody want me to go ahead into detail on this? I'll just take that as a no. So we're going to cancel all of these and say, thank you, technology. And they came out with a p-value very, very low, less than 1 out of 10,000. It's not too shocking since one had a high percentage over 10% and the other one had a percentage of 1%. That seems evidence to support that the states don't have the same proportion of one plate illegal drivers. So they do talk about the idea that we could have found a test statistic here, but we only have about 7 minutes left. So I'd like to go ahead and see if we can segue at least into one quick look at an assignment problem. All right, so here's what they look like. And as we've seen in earlier problems, they'll first ask you to set up the null and alternative hypotheses. So in this case, we have, it says, since an instant replay system for tennis was introduced at major tournament, men challenged 1391 referee calls with the result that 418 of them were overturned. Women challenged, so our two populations are male versus female tennis players. And the women challenged a certain amount and had a certain number overturned. Use a 1% significance level to test the claim that men and women have equal success in challenging calls. So our null hypothesis will always be that the two proportions are the same. And in this case, the claim that we're testing is that men and women have an equal success. So that is the null hypothesis. So the alternate would simply be not equal, which in this case looks like that is F. So then right off the bat, they want the test statistic. So I'm going to go to StatCrunch. And we're going to go to proportion stats. And now we finally get to use the two samples. And in this case, they gave us a summary of the results. So with summary. So now we're going to the two sample. And so like we did when we did one sample, we have to put in the number of successes and failures. Population 1 was the men, which had 418 out of 1391. Population 2 was the women, which had 227 out of 747. And our hypothesis test is the default, the null hypothesis, difference is equal to 0, alternate is not equal to 0. That's what we want. And we're supposed to test this at a significance level of 1%. So, I don't have to worry about that. We're not making it. We'll just do that, compare that to our p-value. So I'm going to compute. So our test statistic is the z-score, which they want us to round to 2 decimal places. So that's there. And our p-value was like 87%. I'm thinking we're not going to get to reject the null here. So the p-value to 3 decimals is big one. And so then the p-value is greater than the significance level, so we failed to reject the null. There is not sufficient evidence to warrant rejection of the claim that men and women have an equal success in challenging calls. Looks like there's more to this problem. So now they also wanted us to construct a confidence interval, because then we can do this with the confidence interval approach. And let's remember that in this tool, I don't need to enter the information again. I can just edit and change from the hypothesis test down to the confidence interval. Now, we have to do that one-tailed, two-tailed test thing that we discussed a little bit at the beginning of class today. So when you have, so because this was a not equal to versus equal to, that's a two-tailed test. That means the error of our significance level, which is only 1%, needs to be split between the two different tails because we're counting both of them. So there'd be 0.5% on the right and 0.5% on the left. And for that to happen, our confidence interval in the middle has to be the other 99%. So for this one, I would change the confidence level to 99%. If this was a one-tailed test and we had our 1% tail on one end and the other one was also 1%, then we'd have a 98% confidence level. Confidence interval. So that's the difference between sort of whether you double the thing or not, as we were trying to discuss earlier. Anyway, something to think about, and we can talk about it more, and we can look at that in the future as well. And I did do that in some example problems, but that gives us our confidence level that they're asking for at the appropriate confidence level. So they want that to 3 decimal places. So I'm going to grab this first one for the left value and this one for the right value. So the thing to notice here is that I didn't even have to re-enter the summary statistics. I just had to change over to the confidence interval thing. So now how do we draw a conclusion with the confidence interval? Well, our null hypothesis is that there was no difference between the two, that the difference was 0. And our confidence interval tells us we're 99% sure that the difference is between this negative number and this positive number. Well, since the confidence interval limits include the 0 value, then there does not appear to be a significant difference between the two proportions. It's perfectly possible, according to our samples and our confidence interval, that there's no difference between the two. So obviously, we can't reject the null with that fact. There is not sufficient evidence to warrant rejection of the claim that men and women have equal success because our confidence interval includes the idea that they might just be equal. So I apologize for sort of going through that a little quickly. I just knew there's a lot of parts here and I wanted to get through it. We have this one last part here to finish up. Confidence level suggests there is a significance difference. There's no significant difference between the men and women. Let's try that one. And that completes the question. So that was number 6 on the homework set for chapter 9. We have now reached the end of class. So I will stop there.